Hi guys, hope you're doing alright. In this video I want to talk to you about the physics of a guitar, sort of applying what we've talked about with waves to concrete examples. So let's get started. This right here is my guitar, acoustic. Uh, First thing I want to point you towards is like when you play a note, the body, this is what's vibrating. And when you have one thing, let's say the string vibrating this piece, and that piece vibrates the body, that vibrates the air, that's what we're hearing, the air is vibrating, that's vibrating your eardrums, that's kind of how the sound wave travels. One thing pushing another thing at the same frequency, that basic phenomenon is called resonance. And yeah, the cool part is like they're all vibrating with that same frequency, that's that wave. My question to you guys is, can you think, this is a guitar, how would you change the sound of a guitar? What are the different ways that you can make sounds on a guitar, or to change the sounds that you're hearing? How would you get different frequencies? So there's a couple ways that I can think of off the top of my head. So you can see right here, you play guitar by vibrating the strings, and you can see that the strings are a little bit different. Can you notice what's different about the strings? This top one is really thin, this bottom one is really thick. It's actually the reverse. This is kind of the bottom one, and this is the top one when you're holding it. So the mass, also the density of the string, that affects it. Another thing you can do, so to play a guitar, this is weird to do with one hand, but you vibrate the string and you hold down the string at one fret. What are you doing when you're doing that? This part of the string is the part of the string that's vibrating. This part is not vibrating, so when I touch it, it doesn't affect the sound. So what am I doing? Actually, when I'm doing this, I'm changing the length of the string, the part of the string that's vibrating. So I can change the length of the string, I can change the density of the string, and let's say I want to tune it. What is this doing? It's actually just like tightening the string. Changing the tension on the string is going to change the frequency that it gives off, the sound of it. Those are the big ones that I can think of. Yeah, cool. Let's take a closer look at why this is the case. Okay, so in physics, we want to try to describe what we see with a model, and in our class, we've been able to describe phenomena in terms of a nice, neat equation. So let's try to derive one for a standing wave on a string. Or recall, a standing wave is a special combination of interference or superposition and a reflected wave and an incident wave, basically interfering with each other in just the right way, where there's complete destructive interference at certain points that happen to be the same. So in the video that I showed you last week, there were patterns that emerged. The simplest pattern on the string was when there was just a node on each end, and then this point that's has the maximum displacement, one of those. I'm drawing a dotted line here to show like this string was vibrating up and down. The next pattern basically was not just one node, or not just two nodes, just a node. This is called an antinode. Don't worry so much about the names, but yeah. So this is the next pattern, something like that. Notice that the length of the string is the same, but we are just adding another node, and we can add another antinode that would give us the next pattern. These are the standing wave patterns that you would see if you just try to keep vibrating this string at different frequencies, eventually you would hit one frequency and see this pattern, and then double it, you'd see this, and then triple it, you'd see this. That was sort of the pattern. Where does that come from? So we can derive where it comes from. If I know the string length is L, you can pause the video and see what is the length. How does the length L, this black line, how does that relate to the wavelength of the wave? So you can pause the video and see if you can derive the relationship yourself. What's the wavelength of this wave compared to L with respect to L, and what about here, and what about here? If you want to try it yourself, take a few minutes, 5 minutes, pause the video, try it, see if you can get an equation for wavelength in terms of L. Okay, so hopefully you tried it. You can see that this right here is a half wavelength. If I was to sort of complete the wave, this is one full wavelength. So right now this is 1/2 wavelength. So that's why I'm going to write lambda over 2. Lambda is the symbol for wavelength, is equal to L. And if I solve for lambda, I get lambda is equal to 2L. Look, doing that same trick over here, from one node to the other is 1/2 wavelength. How many half wavelengths are here? 1, 2. This is one full wavelength. In this case, lambda is equal to L. What about here? 1, 2, 3. So we have 3 half wavelengths, and that is equal to L. This one, if you can, I could write this in a very suggestive way. It's 2 half lambdas is equal to L. You may see a pattern here. 2L over 3. If I were to say that this pattern is called n equals 1, this one is n equals 2, and this was n equals 3, and so on, you would see that I can write lambda is 2L over n. When n is 1, you get 2L. When n is 2, you get lambda is equal to L. When n is 3, you get 2L over 3. So this right here, this is the first wavelength, and there's an associated frequency. I don't think I showed you the equation before, but there's an equation that relates frequency, wavelength, and speed, the speed of the wave. So that general equation is V is equal to F lambda. I think I did introduce it to you. Basically, the speed of a wave is the time it takes one wavelength to move. So if you know one wavelength, and if the period is defined as the time it takes for a wave to move one wavelength, then if you take wavelength divided by period, you'll get V, and 1 over period is frequency. Wavelength over t is equal to V, and a period is defined as the time it takes a wave to move the distance of one wavelength. So you're getting distance divided by the time it takes to travel that distance, that's the speed. So that's where this equation comes from. If I combine this equation with this, let's see, F is equal to V over lambda. So the frequencies here are going to be F is equal to V over 2L. F is equal to V over L. And F is equal to 3V over 2L. And the general equation here would be, let's see, sort of rewriting this in terms of F, solving for it. Yeah, so F is equal to N times V over 2L. That's our equation for frequencies. This is the one we want to hone in on, because when we're hearing the frequency, when we're hearing the pitch of a note, we're hearing the frequency. So what is this equation saying? It's saying that for this fundamental frequency, you're going to get a frequency of V over 2L. and the next highest pattern is just going to be double that frequency. The next highest pattern is going to be triple that frequency. So that's what you're hearing. What I showed you before on the guitar was changing the length, change the frequency. But also, like, if we were able to change the speed, we would change the frequency. There's another equation that tells us what affects the speed. It's the properties of the medium. It's the square root of tension over the mass density, the mass per unit length of the strings, of the guitar strings. This entire thing is for talking about standing waves on a string. I don't know if you're able to follow along with the derivation, so I'm going to just kind of summarize. This equation nicely summarizes the frequencies you get, the standing wave frequencies you get on a string that's vibrating. The video I showed you last week, you just take a string and vibrate it by hooking it up to, let's say, a speaker. When you change the frequencies going from 0 hertz to 1, 2, 3, 4, 5, for some given length, you're going to see that standing wave pattern where it's like a wave that looks like it's vibrating in place. And when I'm playing notes on the guitar, that's what I'm hearing. I'm hearing those standing wave frequencies. And that's kind of the gist of the physics. I want to return back to the guitar to kind of show you some cool things. Yeah, hope you're able to follow along. Okay, so I showed you the equations. I want to just, again, connect it to the actual application here. When I'm playing this string by itself, it's called open E. That's a certain frequency note. I should look it up, but I don't know what the hertz is. But let's say the hertz is something like 600. If the pitch of the sound goes up, the frequency also goes up. Right now this is an open E. If I go through this scale, E, F, G, A, B, C, D, E. This right here, this is what the 2 dots are. That is the 12th fret, the fret being the space between the markings. So this 12th fret is also an E. And you can kind of see it visually. This is the halfway mark for the entire length of the string. So the open string is an E, and when I half the length, I'm also getting an E. But this E is of a higher octave. And that relates exactly to the equations that we derived. The other thing I wanted to mention, something that I learned recently just from kind of investigating this. It's kind of sad. I've been looking at physics and especially applying it to guitar, but I learn more. I'm not really an expert with guitar, but key idea. When I'm playing this, I'm not hitting just that open E note. I'm not hitting just one frequency. There's multiple frequencies. Normally when I put my finger over this, you hear the sound. That's the 12th fret. If I lightly put my finger on the string, so I'm not really pressing down on it, it still vibrates. That doesn't happen at other spaces. It comes out pretty muted on most other spaces. But over here, because this is sort of a special interval of the standing wave, of the length of the string, this is the halfway mark, what you're hearing is that higher octave E note. That higher octave note on this open string. And that's ringing out when I play this open E note. It's more subtle. But by putting my finger over here, I'm sort of muting that larger frequency wave that's vibrating the entire wave, the entire string, and I'm only allowing that higher frequency standing wave to ring out, and that's going to play out in this other video that I want to share with you. That's kind of what I want to show you. Oh yeah, so this is called a harmonic. It's there for each of the strings, and I believe it's like, yeah, it's on the 7th. It's also on the 7th fret. You're getting those harmonics because the 7th, I think, is also some nice fraction of it, either a quarter of the length of the string or 2/3. I forget, a third or 2/3, one of those. So you would expect, to get kind of a harmonic somewhere over here. Because you're getting those fractions of the entire string. My main thing to I'll actually just wrap up there. The takeaway from this is there is some physics going on behind not just this instrument but other instruments. Oh, I want to share with you one thing. It's kind of a fun demo, and it's a straw. Let me set it up properly. Okay, so one pattern I want to just point out, I don't know if it made clear, was this string. When I shorten the length, what happens to the frequency? Does it go up or down? And does that agree with the equation that we just derived? The equation is F is equal to NV over 2L. So when L goes down, F goes up. So by shortening the length of the string that's vibrating, the frequency is going up. You're hearing it go higher in pitch. That also applies to not just string instruments, but there's a similar set of relationships that you can derive for woodwind instruments, brass, things that vibrate, that you breathe into. You can test this out with a nice little straw, plastic straw. If you cut the edges of it, let me see if you can do this. If you cut the edges of it so that you're getting this V, getting a nice V. That should do it. I don't know if you guys can see that. Getting a nice V. If you kind of bite it so that those ends of the straw are closer together. And you blow into it, you can get this reed effect. So they're pretty close together. It's kind of late at night, so I don't want to blow too loud. So you're seeing that, right? You're hearing a note. What do you think's going to happen when the length of the... Right now it's the air column in the straw that's vibrating. What do you think's going to happen if I reduce the length of the vibrating air column? Is that frequency going to go up or down? Pause the video and predict it. Okay, let's try it. Okay, I don't want to wake up my neighbors, so that's physics applied. You can apply that to the strings on a piano or other instruments. The key idea is that there's some underlying physics there, and you have some concepts there to see what's going on. How can you change the frequencies that you're hearing? There's more to it. I'll post a video that kind of goes in more in depth than I can share with you. Hope you enjoyed that video. Take care, guys. Bye.